Alrighty, so this is episode 3, I believe, of the Rapid Reflections podcast. Today I'm joined with Taj and Radee.
Good day.
It's been a while since our last one, but today we're going to talk about the relationship between maths and physics. So there's quite a few elements here that we're going to be discussing. One of the elements is sort of the similarities between maths and physics. So first, maybe we'll look into the physics itself. So physics is quite a big sort of umbrella field. We can actually sort of subdivide that into
That's right.
several,
Has
several
quite a few sectors. Yeah.
Exactly. I guess we can start off from the theoretical side of the physics. So you'd first have what we call a mathematical physicist, who is different to a theoretical physicist, even if the culture sort of thinks they're the same.
I definitely would have put them pretty much together.
Say like mathematical and theoretical usually considered as an umbrella term, but actually the roles that they play are significantly different, and the mindsets that they each need to possess to satisfy the criteria for each job is actually significantly different.
That's
as
right.
well. And moving on from these two, you then have sort of computational physicists, and alongside them, their counterpart would be an experimental physicist.
Yep.
So a computational physicist would be
Exactly as it sounds. Yeah.
Really more about computing results based on the theories that we've sort of established, and these theories, of course, have come about due to the efforts of both mathematical and theoretical physicists in different ways, as we'll discuss later, and experimental physicists then verify whether these numbers which have been crunched agree with the world around it. And of course, as you'd expect, experimental physicists have a significantly different mindset that they need to be attuned to compared to the other kinds.
Yes. We should note also, historically speaking, it kind of flows the other way.
It's true.
So experiments, at least when we talk about quantum, right? It's like all of the theory started being developed as a result of some brand new experiments.
Of course, it is like a feedback.
Yeah, they feed through each other in all the different directions.
That's right. It's not necessarily just a linear chain.
From the maths down to the experiment, kind of flows back the other way.
Because different aspects of it can inform the other parts.
That's right.
So on and so forth.
But I guess computational, they're pretty much sole focus is just crunching numbers to verify experiment
Models
using
based on the theory.
using theory.
Yeah.
That's right. And I guess one example you'd compare them to would be to applied mathematicians, right? There might be a sort of side comparison to computational physicists to applied mathematicians.
That's right.
And there might also be a comparison between mathematical physicists and pure mathematicians as well.
You could even
sort of sideways comparison
right.
between the physicist classification and then to
the
mathematical classification. And then, of course, you have the statisticians elsewhere when it comes to other things.
The statisticians are kind of already applied,
maybe,
but they're already kind of applied in some stuff.
Actually, statistician might actually have like a link to the experiments, as Thomas said, specifically because one of the applications of statistics is risk assessment, for example, and data collection based on the real world.
Yeah,
sure. So that's what it's founded on. Yeah, that's right.
And the counterpart of the statistician from maths would be the experimentalist, because they actually gather data and also assess risks and do other things. So I guess there is a certain counterpart between each thing in the physics and anything in the mathematics as well.
That's right.
Which have their own flows, but also interconnections.
That's right.
But that being said, a lot of people actually sort of make this sort of sweeping generalization that physics is really just like applied maths. And while there is elements of applied maths that appear in physics, what we'll, I guess, explain is that there's a bit more, differences than just that on the surface. So I guess let's start at the mathematical end, right? So what is the role of a mathematical physicist in this sort of like hierarchy of physics jobs?
Or I guess chain of them. Yeah.
The chain of them. Yeah.
All right. So let's start off with the role of a physicist, or of both theoretical and mathematical physicists in general, is to sort of come up with models that come up with mathematical. The reason we use maths, of course, we always think about as numbers. Numbers, if we allow a significant amount of decimal places, are a precise way to describe things in our world.
Sure.
We can describe things using words, we can describe things using other descriptions, but numbers is just the most precise format.
Yep.
And it's for that reason we use numbers to describe our world. And the objective is to come up with relationships that our world satisfies in terms of numbers.
Yeah.
Right? And these relationships are usually called equations. Right? The job of a theoretical physicist is to come up with some sort of equation which gives us the ways that our universe exists or evolves, depending on sort of the picture you want to sort of view it as.
Yep.
And their objective is to find the models,
Yep.
right? The mathematical physicist is someone who actually needs to understand a significant amount of mathematics, because their objective is to sort of have a deep understanding of what the tools that mathematics provides us is. Right? They need to have a deep understanding of what is available, what relationships exist already in the numbers themselves as we've defined them.
Yep.
And with that deep understanding and so on, they put constraints on what equations are possible to be used at all.
Yep. And then the theoretical physicist, given the, I guess, narrowing down of what equations could possibly be used, they would then pick from that, reduced pool.
That's right.
And then give those a go and see whether they can come up with a model that actually, closely resembles reality. But they can't, verify that themselves. They'll have to come up with a model, and then I guess that job will be passed further down the chain.
That gets fed back through.
The two people who'll be verifying. I guess that's the computational physicist, and then
alongside
the
with
experimental.
Yes.
So I guess the computational physicist would directly take those models and equations that the theoretical physicist had come up with, and they would do what they can to solve those equations and translate that into your computer language.
Yeah, that's right.
Code it up, solve it, and then come up with some prediction for what those equations.
I guess it is at this moment that the equations that we are supposed to use for a physical world are come up with by the theoretical physicist, right? But then the solution methods, which is I guess the different techniques such as finite differences.
You got all the numerical schemes.
Sort of numerical solution.
There's a gigantic list of them.
But, and these things are usually come up with by applied mathematicians, though, right? So the computational physicists, as we've talked about previously, they can themselves come up with new methods to solve the equations.
Might do,
true.
yeah.
But I guess their main attribute to it is the computing of the solution.
That's right.
The solution method is given by an elsewhere branch that physically focuses on mathematics, and which is the applied mathematicians who find the
making making algorithms.
Right, and then they implement it in the code itself. And that's what the role of the computational physicist would be in that sense. Right.
So I guess similar to how the theoretical physicist would pick from a reduced subset of possible equations to create their theory, the computational physicist will pick from a list of algorithms or numerical recipes that they could use to solve the equations that the applied mathematicians would have developed.
That's right.
And have to find one that perfectly fits their problem that they're working on.
That's right, which will optimize the solution for the required application. Yeah.
Right. And as we're actually discussing all these things, it's remarkable how we're finding these relationships between these different relationships and analogies between these different sort of branches of physics and mathematics.
That's right.
We're sort of going through this podcast, right?
Yeah.
This is the kind of thought process, I guess, is one way to describe what mathematical physicists and theoretical physicists would have in common, because mathematical physicists would sort of look at different areas of maths and see how they sort of relate together, analogize them, and combine them together into sort of one cohesive theory.
That's right.
How different examples is sort of a part of one big theory, and once you understand one big theory, everything is an example.
You just apply the example. Yeah, that's right.
Everything
Repeated application.
Right. Yeah. So this kind of bringing together different areas into sort of one picture, and how they all have structures in common. This is the kind of thought process, as we've actively demonstrated.
Yeah, that's what you're describing is exactly what pure mathematicians do, right?
Right.
Yeah,
that's right. That's one of the main
generalizing structures, then applying to lots of examples.
Right. There's certain things like when it comes to computations, a lot of people would be given a certain problem to solve, and they'd spend weeks or maybe even years, months, and then years to solve the problem. But if you had developed it properly, then you could have developed a general theory for it, which would have solved 1,000 of those problems, and then you could have plugged in your.
That's right.
And you could have done this only by understanding how the problem you're working with relates to other problems.
Yes.
And then you could have
which might even be simpler potentially.
Like a cohesive.
Yeah.
And this kind of thing is also present in the theoretical physics way, because they have to look at a lot of these different models that already exist or may not exist, and look at their similarity and differences, and then they sort of
even analogizing in physics, let's say how this physical phenomenon relates to something else you might have studied.
Exactly.
Say, yeah.
Exactly. I mean, that's
Yeah.
that kind of
That's maybe what
that
the-
kind of leap is what the theoretical physicists want, specifically related to the real world. As
Yes.
opposed to
Yeah, I think we've
numbers.
defined now then the clear distinction between mathematical and theoretical physicists in that sense,
Yeah,
Yeah,
mathematical
because-
physicists would look for constraints in the numbers themselves.
and the governing equations,
And
Yeah.
and then as opposed to theoretical physicists
This is
who's
like making analogies to reality to try to fit the maths
that's
to
right,
it.
using potentially pre-existing descriptions that might be there.
Yeah.
Say, like I don't know, extending equations, let's say classically to for quantum or something like this.
Right,
Yeah, you could
right.
say that's theoretical physics.
Yeah.
Yeah.
I guess going more deeply into the theoretical and mathematical, one of the things we should describe is sort of the way they're treated in sort of university level education, for example, because
yes.
the culture that sort of informs us in that setting makes us have a certain perspective on how these two different types of physicists are supposed to be.
Mm-hmm.
For example, I'm pretty sure this is what they do in most places, not just the University of Adelaide where we're from. They make it seem like you should do a lot of these maths courses as a co-requisite to the physics courses that you do.
Yes.
Specifically, if you want to become, for example, a theoretical physicist, there wasn't really much talk of mathematical physics. Most people just assume they're the same thing,
Yes.
even though I guess University of Adelaide has a history of killing.
The department.
Yeah.
The Department of Mathematical
I mean,
Physics.
all that's left in that department's a cardboard box with text and textbooks in it.
Right. That's right. So, I guess can you guys, maybe describe sort of the kinds of courses that they might have told you to do, and then relate that the kind of maths courses they said would be useful for your physics, but then they may not have been as useful because of certain reasons of difficulty.
Yes.
And ease.
So I mean, this is probably I don't want to repeat from Wesley and
Yeah.
I's podcast because we
Yeah.
kind of touched on this, but I guess because I've just finished this critical
Yeah.
year where it's become obvious.
Yeah.
So the courses are when you take your first analytical mechanics course,
Yeah.
as in Lagrangian mechanics, Hamiltonian mechanics, and then you take your not first, but a proper quantum mechanics course. It becomes clear then. What do they tell you to know? Well, for the analytical mechanics, it would be good to know, a bit of differential geometry, maybe a bit of group theory. When I say bit of, probably you need to know it a fair bit, obviously,
Yeah.
but
Mm.
and so for that, well, differential geometry, we don't have that in undergraduate. That's one thing.
Mm.
Group theory, you do it on the pretty basic level.
Yes, right.
Um,
And you basically do finite groups, right?
You do finite groups, yeah,
You
which
do,
are-
you do finite groups in group theory, but the real groups you need to understand analytical mechanics or Lagrangian mechanics / Hamiltonian mechanics,
and even
is-
then quantum
is
as
Lie
well
groups.
is Lie groups.
Is Lie groups,
yeah,
right?
yeah,
So,
yeah.
and Lie groups is
It's a
like,
big jump.
yeah, it's like
massive
it's
jump.
Yeah, that's right.
Grad level courses to do those.
Yeah, and
That's
even
right. But even then,
even
like,
grad
it's still
levels-
active area of research.
Yeah,
so,
even
yeah.
grad levels don't do justice to what Lie groups is supposed to be.
Yes.
Supposed to be about. So as you can see, the level of physics, the level of mathematics you need to do physics, even at like an early undergraduate level.
That's right.
is
And even
far
some other
greater.
universities, they're doing Lagrangian mechanics, let's say in second year.
That's
not,
right.
not in
that's right.
third year. Yeah.
That's right. So
Yeah.
I mean, it's far, like the jump, the divide is very great. Right?
That's right.
The mathematics that you need to be sufficiently proficient with the stuff you'd use in physics
Yes.
is far greater.
Mm.
You might even consider them to be like 2 levels greater. Like if you consider like undergrad, grad, research level.
Yeah.
Sure. Yeah. It's
So,
yeah.
like-
That's right. Yeah.
Like you need like research level mathematics to do like undergraduate level.
Yeah, literally classical mechanics. Like you'd
And when we
think
say do,
that's
we
like
don't mean. I suppose
simple
yeah. This is
physics.
something. So actually, becoming a proficient problem solver, let's say, actually doing, let's say, Lagrangian problems, doesn't necessarily require. It kind of requires a know-how specifically, like
Right.
setting up systems, coordinate systems. You know what's going to be moving where. You might need to know, have a bit of experience with solving problems, as opposed to, I guess, what we're talking about now is actually understanding the development of the theory.
Right.
Yeah.
I guess that is sort of.
That's
You don't need to know all the deep mathematics to be proficient in those areas, as you've said, because it requires a different kind of know-how. Like
That's right,
yeah,
yeah,
more
yeah.
practical, like because something that's quite thing is like we always sort of talk well about people who understand the general theory, and then you sort of apply n equal to 4, and then it's sort of easy.
Yes.
But sometimes the application of the n equal to 4 is in itself like a hard thing as well, and that
That's
requires some experience to sort of do, right?
Yep.
Understanding the general theory of black holes doesn't mean you are proficient with, for example, a specific example of a black hole, like the Kerr black hole or something, you know.
Sure.
You don't know too much about it, or it might take you some time to solve
Actually, so go through the process. That's right.
For that thing.
Yeah.
I guess the issue is that in the physics courses where we did the Lagrangian mechanics, they sort of tried to cram everything together. So not only did they try to teach you the methods to solve those problems using the Lagrangian formulation, they also tried to do all the maths behind it. But because at that point we didn't know much of the maths required in order to actually do those formal derivations, they had to do a lot of hand waving procedures, brush some things under the rugs, skip over some results, so then it actually wasn't really satisfactory at all.
No, and it kind of, this is the main thing I took away, is it confuses you even more.
Yeah.
Like you actually, as opposed to aiding the explanation or my understanding, I actually get kind of blocked when you do this weird hand wavy thing that just confuses me.
It's like they're confused of what the main point of that course sort of really was. I think if they distilled it down to just saying, all right, let's just teach you guys the algorithms of how you would solve a classical mechanics problem using the Lagrangian formulation. That would be a fine course.
Yeah, because you'd be getting intuition for solving problems, which is a big part of, as we've just talked about before, actually being a physicist.
That's right.
On the more practical side, let's say.
Yeah.
Because we had like the theoretical side and the practical side of both of the...
So you're saying it's giving you more practice in sort of dealing with all these problems.
That's right. But I guess what Tom was trying to say is because they're trying to do them both, you kind of get bogged down when they give you the theoretical, I say theoretical quote unquote, aspect of it, but it just confuses you, which means it hinders you from actually developing your practical skills even, because you just get confused.
Yeah, it's a bit of a one-size-fits-none.
That's right, yeah, and I imagine you guys have roughly the same thing to say. I mean, we did all the same courses, I suppose, so.
Yeah, exactly. I mean, it's, but yes, although the levels are different, they usually for different things, but because they try to do everything, both of them, all of them in the same course, that's why there's a sort of issue, right?
Yeah.
Big one, yeah.
But I wonder what the sort of solution to that would be. Like, what approach should we take then? Like, what's the best way to sort of, teach some people the practical skills of, being able to compute the solutions of problems really quickly.
Yep.
Whereas, I guess for others, or maybe the same people, we want them to have a deep understanding of the maths behind it.
So one thing is to raise awareness of these different aspects, which wasn't clear to me at all what they were before. Like, let's say a few years ago, I would have absolutely no idea. Like, when you say physicist, you just mean this big general term which covers all bases.
Right.
Right.
And you usually associate the word physicist to someone who can also do maths very well.
And probably does experiments, maybe.
Yeah,
like the guy's a god, he does everything, basically.
Experiments, or a lot of high level in mathematics.
And coding.
Yeah, and then I guess when you first encounter these people and encounter the different kinds of these people, you might get disappointed, or you might get angry even that, like the picture you might have had of these people is not what you get.
That's right.
This person can't do maths. What did I expect?
That's right. But that's only because I think of a lack of communication in the system itself, which provokes that. So that's first step, is to make clear, like, what are the different ways of thinking in this big branch that we call physics. And then I think that will help us to start putting people on the track that they think they would like more. Because then you can start sending people to do, let's say, more maths. And just tell them, wait, hold up, buddy, you need to do a fair bit of maths before you can start doing the physics properly. As opposed to, let's say, the more applied guy, just get him in there and start solving problems without worrying too hard about all the details, right?
Yeah, because you don't need to know everything. I don't need to know how a car works.
To be a good driver. To be a race car driver.
Those details are sort of
That's right.
useless.
That's exactly right.
Like,
so it's the same thing with, let's say, like solving problems in classical mechanics, maybe even solving problems in other areas of physics. Like, you just get proficient at setting up problems and solving them.
Like, that's right, yeah. I mean, because I might know all the sort of advanced different geometry on formulating Lagrangians on jet manifolds, but if someone gave me, like, look, there's like a spinning top.
This weird system.
A spinning top on another spinning top, set up the, the system and then solve it, I'd be like, oh, well, okay,
That's exactly.
I'll give you some time. I'll just sort of set up the.
That's exactly right. And so I think that's why, and that's actually another a bad rap that mathematicians get also, like, you know, they might just be doing pure maths and then some guy asks you, well, why don't you solve this problem then, big guy? But it's like the actual way of thinking, it's not the same way of thinking.
Yeah. You know, like, you get a press as a mathematician, you're like, oh, like, if you're like so...
You don't do anything.
Like so general, then why don't you just solve
this like very concrete problem.
That's right,
in like 5 seconds. I'll be like, well, I mean, I can tell you that the solution can be solved.
That's right, and it's a unique one potentially, yeah.
It's a unique solution, and I know all the different possible ways to do it, but it'll take me some time because
That's exactly right. And so I think
practice.
Yeah, bringing awareness to that, I think, would be probably one of the first big steps, just for everybody.
Yeah.
And this actually, now that I'm saying this for physics, it technically also goes with maths as well. But at least I think the mentality is a little bit more clear in maths than it is in physics.
Mm-hmm.
But yeah.
Because I think the problem is that by trying to have, you know, a general physicist to wear all the hats, you know, your mathematical, your theoretical, all the way down to computational, experimental.
That's right.
For them to do all those things sort of like makes them a little bit worse at everything. Whereas,
That's right.
You know, specialization is one way that we can get, you know, people really good at a certain task. So then you have a collaboration of people who are good at their individual sort of subfields.
Exactly.
And then that problem gets solved in a much more an efficient manner.
That's right.
And as a society, specialization is why we've sort of improved so much, right? But I guess the Achilles heel of specialization is like the communication. Right? So
yes.
the communication is significantly lacking. And the other human attribute that sort of goes against specialization is the supposed artificial prestige associated to some branches of physics as opposed to others. Like there's for some reason some association of the theoretical or mathematical to be more of a smarter or a higher level, intellectual versus, you know, like the experimentalists are seeing more of the grunts in the sort of stream of things, but that's not the case, right? So if everyone really saw these different things as actually just different as opposed to
in a hierarchy,
and you know they focus on their own thing and they were open about the communication and helping each other out in whatever way they could. Then we would do much better.
That's right.
You know, like the theoretical physicist attempting to explain it to experimental physicists and be like, this guy is stupid. Like, I'll just explain it even worse for him.
But I think, you raised exactly the point. It's like, they might look at it, let's say an experimental physicist say, they don't know any maths, they must be stupid. But actually, experimental physicists solve very different problems that, you know, a mathematician probably might not even like sort of concern themselves with.
As Taj was saying before, that's exactly right. Yeah,
this a classic example with, let's say, you know, the photoelectric effect, right? So
I love it. Yeah.
How do they, you know, measure the kinetic energy of those electrons like that?
They get emitted by
and it's actually kind of hard to measure the kinetic energy of like, you know, an electron or like at least the maximum energy one.
A naive approach would be, look, we want to measure the maximum kinetic energy. We could, I guess, track the beam, like how fast it goes from one point to another point, and then sort of calculate the speed in that way.
Just like
but, you know, like how would you march these points, and how would you measure that distance? They're so small, and
that's right.
All this stuff is sort of comes into the naive approach, and you know
that's right. But then, what's the punchline, Tom?
You got your big brain approach of like you apply a voltage sort of against the direction of the motion of the electrons, and you keep cranking that up until the potential sort of slows down the electrons until they just stop.
That's right.
So you want to sort of keep cranking that voltage until you don't see that current anymore. And the moment, you know, that happens, you know that you've just put in enough energy to stop the energy of the highest energy electron.
That's right.
Yeah.
So then you know that's the energy.
That's the energy. Yeah, there you go.
Like controlling something you can control, like the voltage.
And simply.
It's very easy to do that. You're able to
just crank them
You're able to determine by the way that they stop, not the direct measurement, but by an alternative sort of method that you come with your big brain, galaxy brain approach to sort of do it. And like, you know, this thinking, like, the logic that goes into it, the knowledge of the tools available, all these things is incredibly intelligent. Like it's crazy, right? So it's nothing like stupid about it. It's just
It's just a different problem.
It's just a different problem, and it requires as much sort of thinking as you need for a proof or anything of that sort. Right?
Precisely, yeah.
So, in a proof you use like tools of maths, your axioms or other theorems, and whereas here you'd use the equipment you're available to, and it's about, finding the right route.
Or even coming up with new equipment.
That's right. Manipulating the quantities you can measure as well, because there's not a lot that you can actually measure. Really.
No, that's right. Yeah, I think... so it's just a matter of taste, really. Like, it shouldn't be about being in a hierarchy. It's like, this guy likes solving these kinds of problems, but this guy likes solving these kinds of problems.
That's right.
That's it. Compare them to each other.
No, that's right. Just like let them both solve their problems and be happy. Yeah,
right, that's right. And I guess but then to improve the communication, we I guess need the people to talk more to each other.
Yes.
They need to be. I mean, when you sort of know a lot about something, you know a lot of finer details, a lot of jargon about it. But your ultimate test of understanding is when you attempt to explain it to someone else
who's just outside of the
after the thing, right? So
outside the field.
I think the culture we want to display is the ultimate display of your knowledge is the capacity to explain it to someone that wouldn't know anything about it. That should be the culture, not the other way around, where the culture is now the less they understand, the better. It's because it makes the thing you're doing
more sophisticated.
Yeah,
that's right.
And you get a sort of pride boost when your thing is ununderstandable because you think, I can understand it, but he can't.
That's right.
So I think the culture should be changed to sort of make people work really hard and put a lot of time into trying to explain it to others, and that'll sufficiently boost the collaboration between different people. And when that happens, people can more freely specialize.
That's right.
Because then they won't have to do all the things themselves.
That's right. Yeah.
Because people probably do everything themselves because they don't maybe trust anyone else doing it properly. So there might be a bit of a pride aspect there. And then thinking, no one else can do this work, so I guess I'm gonna have to wear all the hats and do that job.
But you quickly see that kind of thing can get you nowhere fast.
That's right.
You're not going to be able to do what's required to advance the field with such thinking. Yeah.
Right. That's right.
So I think
this actually applies for all fields, across the board, irrelevant of what we're talking about in actual fact.
Not just physics.
Yeah, this is literally anything you can think of. Same thing.
Yeah, I would say the number one most important thing in science right now is communication. You could be the fattest researcher in the world, coming up with new theorems on a daily basis, like fantastic, mind-boggling proofs.
Yep.
But if you're not able to communicate it to anyone, no one gets the novelty and the importance of your work, then you would have kind of wasted your time.
They'll spend their time re-getting the results that person might have gotten.
Yes.
Right. So
because it wasn't clear in the first place.
They didn't understand, so they'll just spend their time, redoing the results that guy got, and that would have wasted everyone's time.
That's right.
That's
right.
Yep.
So yeah, communication is the most important property that humans have in general that makes us so successful. So that's why we need to definitely focus on that.
That's right.
As the priority on any sort of matter, not just science.
Oh, it's literally key axiom for existence.
Key axiom for existence.
Even on a daily
basis,
right?
Any level you care to speak of, for sure.
Yeah.
So I guess that is sort of, in summary, the hierarchy of or maybe not hierarchy is the good word, but sort of the relation between all the different subfields of physics and how they should really all work together, communicate so that they can specialize in their respective domains, and that altogether will sort of advance physics as a whole,
right?
And how it sort of fits into the maths as well.
Actually, going back to a certain point, when we were talking about how exactly to make the maths align with the physics, what would we do? Would we have a separate stream for mathematical inclined physicists versus a separate stream for theoretical ones? What can we do to sort of bridge that? Should we have better maths teaching so we can teach the maths faster? Or should we have a different stream for people like that?
Because right now it's quite difficult because of that massive 2-level gap between the maths you need and to do the physics you want to do.
And most of the lecturers who've suggested you should do these subjects, it'll help you with your physics, are under some sort of misconception that doing basic complex analysis or group theory is going to be very
somehow.
paramount to what doing quantum field theory and solving PDEs for some reason. Like, whereas like understanding the real theory of PDEs and how you sort of deal with it is like much later. If you ever
If you get around
if
to
you
it.
ever do that anyway, because most people, because like most everyone's broad level of education ends at undergrad, because then you sort of specialize into sort of
That's the
things,
benchmark now. Yeah,
and so like you'll never get to the research level,
that's right.
right? So I don't know.
Yeah, so I guess you're gonna need physicists who can get away with knowing no maths. You're gonna need physicists who can get away with knowing some maths. And you need physicists who need to know a lot of maths. So that's just the way I'm thinking about it.
Yeah.
So basically, maybe for some of them it would be good for them to have some exposure to the concepts, but not necessarily like
an
in-depth understanding.
Right.
So,
but I guess the thing is, like, you still need like the physicists that know maths, for example, right?
these are experimental physicists.
So there's like, or maybe not no maths, sort of maybe the middle ones, the middle tier ones. So you've got the mathematical physicists or the mathematicians. They know all the math, know all the sort of big theorems and are very deeply attuned to them, right?
Yes.
Mm-hmm.
They then communicate with the one physicist that might not need to know as much of the maths, and they use certain analogies or somewhat.
Well,
like
let's
that
call
to-
them. We're calling them theoretical physicists.
Let's
right?
call them theoretical physicists.
Yeah.
They use some analogies and somewhat like that to explain the sort of result to them, and then the theoretical ones, communicate to the ones that require even less. But at each level of this, a certain amount of understanding is lost. Right?
Yes.
So
always. Yeah.
Yes, a certain amount of understanding is always lost, right? And then after a certain stage, whatever was said originally is gone.
That's right.
Right?
Yeah.
And one example is, for example, in physics, they always talk about locality. Like the
What was that again?
So like the laws of physics. So laws meaning equation which constrains what the system can be, right?
Sure.
One of the things is it's supposed to be local. So it means like an equation is just an equation for unknowns, right?
Mm-hmm.
You can think about if your unknown is a quantum field, you can, I guess, think about that quantum field in terms of particles, excitations,
Sure.
and if the interactions between these particles are localized in a particular region, we call that localized.
Okay,
the equation is localized if the particles which come from the quantum fields for which that equation comes from has local interactions, right? That's kind of like the physicist picture of what locality means, but it's kind of loose because sometimes locality means like in a neighborhood, other times locality means at the point,
Right.
which I guess is actually mean completely different things when you think about it mathematically.
That's right.
Infinitesimally at a point versus on a neighborhood
A
of
region.
the point is actually very different.
Mm-hmm.
Like in relativity, like for any metric you can find, for any sort of metric you can find coordinates so that the metric at a single point is the Minkowski.
The
But
flat-
to find it
the
on a
flat space
neighborhood,
metrics,
you
yeah.
need the curvature to be zero.
Yep.
There's actually a significant difference between at a point and the thing, right?
And neighborhood.
But speaking of locality, all theoretical physicists will be like, look, we need the laws to be local, a very loose definition of what local means. But the math, if you talk to a mathematical physicist, they'll be like, look, local is actually quite clear. An equation is local if and only if it's a PDE.
All right.
So any because a PDE is an equation which involves the values of the function at a point and the derivatives of the function at that point.
Which is
the derivatives of the
neighboring.
function at a point encompass the information that function holds on the neighborhood of that point, right?
Mm-hmm.
And there can be other equations like f of x is equal to f of x plus 2, for example, that equation.
Yep.
So that gives you a relationship between f of x at the point x, and it gives you a relationship between f of x at another point, x plus 2. That's not a PDE.
Yep.
That's like something else.
That's right.
Of course, most people would never have seen an equation like that, right? So those equations are not PDEs.
Yep.
They're not local,
Sure.
right? Whereas for it to be local, it needs to be a PDE.
PDE.
It's a theorem.
Yeah.
Any equation or any operator whose output depends only on the input on a neighborhood of each of the outputs evaluated points has to only involve derivatives.
Right.
That's a super theorem. So
That sounds massive.
so
Yeah.
the mathematicians would know about that. Physicists forgotten, right? So
Yes.
then
Maybe not by the mathematical physicists, though. Let's say ideally.
Ideally, not by
Yeah,
mathematical physicists.
yeah.
There are some mathematicians themselves don't know about it for some reason, but that's sort of an education problem. But yes, they would know about it, and then they would use this locality
analogy,
in loose ways, and then they would use it, to like justify why quantum field theory is needed, because it's a mixture of special relativity and general relativity. Special relativity and quantum mechanics. Quantum mechanics. They'd be like, they'd use some loose definition of it, and they'd use some other analogies, and it would sort of, as it passes down the chain, it becomes worse and worse. No one knows, and because the prevalence of theoretical physicists to like the lower levels of maths are more prevalent, the culture will then all forget.
Yep. No, I see.
So,
although that theorem in particular, that seems like a pretty absolutely crystal clear.
It is a crystal clear one-line theorem, which is a super theorem.
Yeah.
An operator, and an equation is just an operator applied to a function equals zero, right? So you can think of every equation like that. So an operator is local, meaning that an operator takes a function to a function, right? So if an operator is L of f is another function.
Yes.
L of f evaluated at the point x. If that depends only on the value of f, the input function, or neighborhood of x, then that L of f must be a differential operator.
Great.
That means L of f must take sort of f to a combination of its derivatives,
which is called a PDE.
Which is called a PDE. That's a crystal clear theorem, which took me a while to find, being a mathematician or whatever. But
great, yeah.
And
as a physicist, I never thought I would have heard that.
Isn't that kind of crazy though? Like even like you familiar with the maths sort of like literature and maths results, it even took you a while.
It even took me a long time. Like I thought it was a niche result. Once you sort of find the niche result, you then come up with a lot of references that they reference, and then it becomes more
like clear.
More open.
Yeah.
But like before that, I didn't even think this was even a possibility.
Man, that's crazy. Yeah.
So yeah, I mean, even in the branch you had, there's lack of communication there, and then of course as you pass on, like I was saying, like once you know this theorem, which is quite simple to state, obviously very hard to prove, but
I can imagine.
but with this knowledge, with theoretical physicists knowing this knowledge, they'd be like, look, I'm looking for PDEs. They will know that what they're looking for is a PDE. There's no other equation they're not going to try. They're going to waste their time with that. They know what they're going to do.
That's right.
That's it.
And the theoretical physicists wouldn't need to have like necessarily done the proof for that super theorem. Say they can just look at that theorem, and then that would inform what they need to do.
Yeah, that's exactly right.
Yeah,
which is, I mean,
but the levels. I mean, it's an easy theorem. Like if I know, I'm telling you, you know, right? But something is going to happen. Like when you tell someone else along the chain that they're going to not know it anymore. Like,
that's right. I think So when you speak ideally, you would say that such things somehow would be mitigated. But I guess practically speaking, I just think, at every level that you move, well, again, we keep using level, but I mean, as you move across the different fields, you'll always be losing something. I think that's just something we have to keep in mind.
It's like an intrinsic error, right? So we need some sort of error correcting,
That's right. So because the actual relationship between them is still pretty opaque, I think that would at least reduce the error in such transmission. But in order to reduce the error to zero, I don't think such a thing. That's not going to happen.
Because we're compressing it. We're losing.
Reduce the error to zero. We just need to reduce the possible error we can have, and also set up checking mechanisms to make sure that we don't lose
the critical piece.
The actual essence of each.
The actual essence of it, what it is, and not have people make certain. I mean, it makes sense why they would confuse infinitesimal with local, because like local, close at a point. It's sort of like very easy.
That's right.
A student might get confused with that, and then he or she takes another class, and then he or she teaches it in their way,
in the same.
And then it
that's
becomes
correct.
Different.
The Chinese whispers game,
but not that we should have one person teach everything, because then we'd have less variation, and less variation equals to sort of less ideas in
general.
That's general. Right. So it's a hard problem to sort of.
I can't. That probably require a fair bit of thinking, and probably a lot of a culture shift, I'd imagine, to get such things to take place. Yeah.
But I do imagine that, I guess one of the possibilities of trying to fix this thing is just to have specialized streams. Like if you want to be a mathematical physicist, you probably want to take courses exclusively in a mathematics stream.
That's right.
And then you just make physics to get that physical perspective.
That's right.
If you're a theoretical physicist, that's like the middle tier one that we were talking about, where you need just a bit of maths.
That's right.
Middle tier only in terms of math knowledge, not in terms of anything else, right?
Yeah, exactly.
Yes,
Just
yeah, that's right.
Slightly less maths, like they don't need to go into things super deep.
That's right.
But it would be good for them to be aware of what structures are
Yeah, because
available.
theoretical physicists would need to have an idea of the theorems that the mathematical physicists come up with, because that's the point of the mathematical physicist, is to make the life of the theoretical physics easier, right?
That's right. Yeah.
They would need to know at least sort of... They wouldn't need to know enough to invent more,
That's right.
but they need to know what's done.
Yeah,
That's right.
and to use those established results.
I think so maybe it would be one of them's research level, the other one's maybe graduate level.
Yeah, in that sort
sense,
of hierarchy.
And then the other ones are just you can stop at undergrad.
Yeah, like
Yeah,
experimental or computational physicists, maybe a undergrad maths.
Maybe they should just take applied maths courses. Like just study applied maths, don't necessarily
do the proofs or
don't do pure mathematics.
learn
algorithms.
And plus, there's no fun in doing the proofs anyway. Like who wants to learn proofs? Like you want to actually do the things, especially with these.
With results.
With results.
That's right. You don't need to go through the whole unless
and when you do force them to go through proofs and examine them on that, they start to hate it, and then
not fun.
They sort of start to hate maths and that kind of thing. And that's
right.
the kind of sort of state that the world is in when it comes.
That's what it is now.
You force everyone to do everything, and then they hate it because they're not interested.
No, that's because again with maths, like we usually talk about it again as some like overarching thing as opposed to talking about it in all of its little niches.
And levels of understanding and
that's
things.
Right.
And we need to acknowledge that not everyone's going to like every single one of those niches.
Yes.
Like, I probably won't do a heap of experiments, but that's fine. Like
that's right.
I could talk to an experimentalist. They might not give two hoots about that super theorem that we just mentioned about PDEs.
Yeah,
but that's fine as well.
That's fine.
Yeah. You don't have to ridicule. You just say, "All right, buddy. Yeah, great."
It's different.
Yeah.
Different. We appreciate different things.
That's
like
right.
like my friend might go on like 100-kilometer runs.
Sure. Yeah.
For fun, and I might be like, why on earth would you ever do that? Run for 13 hours straight. But it doesn't make him like better than me. I mean, I guess in terms of like running maybe, but not in terms of like position. Person. So you sort of appreciate it as it is. You're like, oh, okay, you like that stuff, fine. Like that's you do that, and that's
in the same way if you like shovel through maths papers or something on the weekend,
and
he's not gonna like he shouldn't roast you for that.
You're like, why on earth would you ever do that? Like, I hated maths when I was in school. Like, why would you actively put yourself through that sort of torture? I would say the same thing. Like, why are you running 100 kilometers? Bro, like,
that analogy is exactly the same in academia, or even in industry, like literally wherever, like just in the culture generally.
Like in this, like, I don't consider myself better because I do math as opposed to running, and he probably doesn't consider himself better because he does running as opposed to math. We just appreciate our differences and agree to disagree on some of the things, but if he needs some maths help and I need some running help, I know where to go, right? So,
exactly.
And there you go, like specialization, like
that's exactly how it works. You help each other out.
As long as the mindset is that you don't think of yourself as higher or lower than the other, and if you do think of yourself as higher or lower than the other, then you're less inclined to actually go and talk to them in the first place. You're like, why would I lower myself?
Yeah, you're reducing your own ability to learn
because of the whole poor mindset.
That's exactly right.
So
so the cultural shift I think would make, at least for a start, the biggest difference.
Yeah. Because that eliminates like your hubris and the pride that comes with thinking that because I know so much about this discipline, everyone else doesn't know anything about that. I'm better than them. And then that in itself introduces your communication barriers. Right. So by knocking that down and recognize that we know different things. I don't necessarily, know much about or enjoy maybe that other area, and you might not enjoy the area I look at, but that's fine as long as we can sort of, recognize the importance of each one.
That's right.
And share the ideas necessary for collaboration. Then you have yourself a
good relationship.
That's right. We just want this kind of clear relationship amongst the people when it comes to academia, for example. And I guess one of the main reasons why we develop this hubris, this desire to be sort of seen to know more than others and all that kind of thing is created in the school system, right? So it's sort of an intrinsic competition from the beginning, right?
Yeah.
So it sort of builds the fact that, and especially the way that maths is treated in school, like people, if you're good at maths, you're smart, and if you're not, then you're stupid, or
yes,
this kind of thing. it builds that you
Yeah.
should be better than others, and some people are better than others, and that kind of thing. And
That's
then
right.
to be able to escape that and sort of understand it's different, it's difficult because of the way it's set up.
Because which
That's
country
it.
was it? Was it Indonesia that had like the two streams?
I was Singapore.
Singapore, sorry, yeah.
Singapore. So Singapore had the system that we had different streams of people depending on what they wanted to do. They wanted to sort of go to university and do more theoretical type things. They might
Sure.
take the one type of stream.
Sure.
Whereas if you wanted to sort of be a more hands-on person and so on like that, and so I guess in that sense you wouldn't want to go to university and learn more theory, you'd want to do more trade stuff, you'd take a different stream, right? Which is great, which is what we're saying, right? We're saying that like
Sure.
Acknowledge what you want to do and
but the problem
I'm guessing what
the
happens-
problem
yeah,
was
yeah,
that was that the culture was poor. Like the
Yes,
the people in the university stream didn't see the other streams as people. Okay,
they absolutely shat on them.
yeah,
I'm guessing,
and
yeah.
plus the lack of interaction with them didn't help. So it just
Yes.
it was terrible, and it built up a culture of segregation amongst them, and so on like that. So
That's right.
so unless we change the culture, we can't try. The
Yes.
stream approach won't work. And
That's
I think
right,
that Singapore is now attempting to do a method like ours in Australian schools, where they still go together, but they get to choose whether they want to be like, they want to do some advanced subject.
Which is surely the standard by now, you'd think. I'm not sure actually, but
I mean,
I feel like that sounds pretty canonical. You go to school for the first few years, you do the same subjects as everybody. Then you go, okay, I want to
Yeah.
pick.
right.
this,
I mean,
yeah,
but
yeah.
I mean, you might think that's like obviously better because you can still hang out with the people from the different streams because there's no streams anymore, and you just choose whatever subjects you want. You might want to do some subjects from the advanced stream, some subjects from.
But the mentality doesn't
But the
necessarily
mentality
change.
doesn't
No,
change.
because
Yeah.
we still
the mentality
have.
still say like you might say like, oh, you have a choice between doing spec maths or general maths, but you don't really. Like
That's right, yeah.
if you choose like the one that isn't expected, then
You get shit on.
yeah, you
Yeah.
get shit on.
Yeah,
So
Which is what happens, yeah. Like
Yeah,
you're taking general maths, you must be dumb.
you must be
Yeah.
dumb.
Yeah,
So
yeah.
like it's like the thing is like we change these. We allow them to sort of make these decisions, but
There's not really a decision.
but the decision
No,
is
no,
not
yeah.
made by them. It's
No,
made
it's-
by the culture. So
Exactly.
so
Yeah, that's for sure. Yeah.
so yeah, that's why it's the main. I guess main thing is like communication and all that sort of thing. It needs to be there for us to have a better culture in this kind of thing.
hmm
Mm.
I think that sounds
Yeah,
like
and
good.
being respectful of differences.
Yes.
Yeah, exactly. I mean, and I guess like, if you are someone who's just been through the school system which propagates separationalist and elitist cultures,
Yes.
and you achieve a professorship or somewhat like that in that pathway alone, then very likely you don't embody the communication and sort of respecting everyone's mindset that we're sort of perpetuating, right?
Yes.
All because the system is geared more towards elitist and
Yeah.
separationalist as
Thinking.
opposed to,
Mhm.
So yeah,
working
it's going to
together.
require a pretty big cultural shift in order for this change to happen. So I guess that's why we're here trying to raise awareness of
That's right.
Yeah,
Yes, yeah.
exactly. And it's not the professors or the researchers today's fault that they feel like they need to be superior to their peers. It's just the
this is the culture
it's
that
just
bred
the
it.
culture that bred it,
That's
like,
right, yeah,
it's- yeah, most of the people that become researchers, they go through a streamlined approach and they don't really understand the world.
They really
Any other way, yeah. Like they get this small little slither from their experiences, and then
or they're just following the trajectory that's sort of almost like dug out for them. Really.
that's right. Yeah.
And it's a trajectory dug out by a culture which surprisingly is counter to doing research and inventing
That's right.
as to
Mm.
what
That's right.
as to what they sort of want, right?
Mhm.
So it's a tough problem, but obviously its system is imperfect. I mean, somewhat by active promotion, but otherwhat because wasn't planned like this, right? It's sort of making it work as we go along,
That's exactly right.
right?
Yeah. So I guess it's actually quite funny. So we started off this podcast episode talking about the divide between maths and physics, and we ended up going to the divide between people.
Right, but I guess at the end of the day, it's a divide between people that perpetuates the divide between maths and physics, because maths
just
and
people
physics
doing
are just things, right?
Yeah, just things
Because
people
it doesn't
do.
have to be maths and physics only, because we're just using maths and physics as a vehicle
Yes.
to sort of illustrate the differences between us that make the divide exist, right?
Yes.
It's like it's not because maths and physics is the smart thing and that's the main thing.
I guess
Or
it's
the
just what we
important
know.
thing.
Yeah,
It's what we
so like
seen.
or maybe it was appropriate that it went into sort of the thing between people, because
That's the general problem.
that's a
actually.
general problem, and
Yeah.
like maths is not like the main thing is meant for so the people in communication, right? The communication between the things is what causes the divide
Yes.
in the thing, right?
I mean,
there's nothing in
in every
maths
case,
that makes it more complicated or more difficult than anything else.
No.
That you need more communication in maths to make it better. You need as much, if not more, communication in other things.
As
Things
elsewhere.
that-
Yeah, if you think about it, like war is like a complete breakdown in communication between like two like countries, say.
That's right. Yeah.
So like most conflicts are born out of lack of
It's
communication.
like communication, yeah.
That's
But
right.
it turns, it is strange. We ended up being a podcast about communication as opposed to one between maths and physics.
I guess that
I think we
that's-
sufficiently elaborated though what the
yeah.
key issues
Yeah.
are. But nonetheless, no, it's good that we went a bit more general.
Yeah, because I guess that we've sort of nailed down that is the problem
That's right.
that has caused that divide.
That's right. Which, albeit, is kind of tautological because kind of we already knew that most problems already stem from like
Yeah.
communication. We
Yeah,
just
that's
we
right,
just
that's
merely went through the process of like unraveling that.
Unraveling
yeah.
the key parts of the lack of communication and how it
Yes.
causes
Yeah.
the divide and somewhat like that, right?
Which is useful because, say, when I was going through my undergrad, I knew there was a problem, but I couldn't know how to like sort of really nail it down. Like, there was that sour taste in my mouth, like something's not right here. I don't know what it
I mean,
is.
this is actually such an incredible phenomenon that people go through. Like, you know, you have a feeling that something's wrong. Like,
That's
you know that there's something going on here. There's something in the air.
Yes, right.
ether.
The aura. Yeah.
You know, like,
yeah,
but
Bad
like,
vibes.
you're just not satisfied until you can sort of solidify it in a word or a concept or something like
That's
that.
right.
You
Yeah,
know,
yeah,
like
yeah.
once you do that, you
That's
just,
kind of what thinking is, isn't
Yeah,
it? Yeah.
yeah.
Like that's.
like you turn ideas into solid words.
I was gonna say feelings.
Oh, to feelings
Yeah, yeah.
and ideas.
You literally take feelings
into
and
word
and you put them into
yeah.
word form. Yeah. Like that's kind of
Into the nuances of our language.
language.
I guess.
Yeah.
Yeah. So I mean, it's
It is interesting though. Yeah.
Yeah.
And for a long time I've had the same feeling. Yeah, as Tom. I imagine you had the same feelings with Taj.
yeah,
Just
exactly.
like
I mean, I
kind
guess,
of bitterness
yeah,
in the back of your mouth.
But you don't know why. Like,
Yeah.
you don't know why the physicists don't know any maths. You're frustrated that they don't know any maths, and then at the same time, like,
You get even more when they tell you should know maths.
Yeah.
Oh, maybe it's just me. Maybe I'm
like
stupid.
they don't know the maths themselves, and they tell you that you should know this kind of maths, and then you're confused, and then you don't have any idea about what you're actually doing and like, where it is and what's going on, and then that's
right.
Yeah.
Yeah, I think. Yeah. Anyway.
Closing thoughts, anyone?
No, I think the fact that we wrapped up so generally is probably a good place to stop. Yeah,
Yeah, I
like
guess
I
so,
feel
you're
like
right,
we were
you're
getting. That's like a good. You reached the
come to the
summit.
peak,
Yeah,
yeah.
Like now we're looking everything from
I
a
mean,
high view.
I mean,
Yeah.
the fact that we were talking about the notion of feelings and words. That's all.
Oh yeah, that's the foundation
yes,
for our.
yeah.
Yeah. So. Yeah, no, I'm happy to leave it there.
Brilliant. Well, I think that is a great place to end off the episode, and
Thanks for listening.
Yeah, thank you, and we'll catch you next episode. Hopefully soon.
Hopefully soon. That's right.
See how we go here.
Yeah. You never know though. But,
Yeah, all good. All right, see ya.